go. All right. Chapter 2 test review. Here's the deal, guys. Lessons 2.1 through 2.6, okay? Just to do a brief recap, what those are. Chapter 2 is all on reasoning, right? So lesson 1 was inductive reasoning. And that was, what inductive reasoning is using what? Patterns, right?
Oh,
Patterns. Inductive reasoning uses patterns, and then deductive reasoning uses logic. That's right. Inductive is patterns, deductive is logic. And conditional statements, okay, we'll get to, that's the if P then Q. Biconditional statements and definitions was, what's the key with biconditional? If and only if. That's biconditional. Then we have the algebraic proof with all the properties of equality and properties of congruence. Then we have geometric proof, right, where we're doing the two-column proofs, and that's what we did last class. You guys remember that? The statements and the reasons. You guys remember that? Okay, so that's a brief overview, but now let's actually go through this process here. So the first thing that we're going to start with is a counterexample, okay? So I guess it should be a conjecture, but by this point we should know that a conjecture is basically like something you're saying. For instance, all boys play tennis. That's my conjecture. And our friend, our brother Marcus here, he's just found his name on my test review. It says, Marcus doesn't play tennis, he plays football. Because it's a counterexample, because a counterexample is an example that proves the conjecture is false, right? So all boys play tennis is the conjecture. Well, Marcus doesn't play tennis. He plays football. Okay, so that's a counterexample. Marcus in himself is the counterexample because he's a boy who doesn't play tennis. Got it? Okay, so that's the counterexample. And in fact, reality is the counterexample isn't this whole statement. Marcus is actually the counterexample. Why? Because he doesn't play tennis. He plays football. So if you guys want to underline Marcus, you know, if you want to highlight or underline Marcus, that might be a really good idea because Marcus is actually the counterexample here. Okay? He's a counterexample. Now, a counterexample isn't always so simple. What's another example of a counterexample? I could say, if x is greater than 0, then x squared is greater than x. Right? And I'd say, what's a counterexample of that? Well, what about if x is equal to 1? Well, if x is equal to 1, well, what's x squared?
1.
1. It's just 1 squared, which is equal to 1, right? Well, is 1 greater than 1? No. So that's a counterexample, because that shows that if x is greater than 0, then it's not necessarily true that x squared is greater than x. Does that make sense? So what's the counterexample? The counterexample very specifically is x equals 1. You don't have to explain it, you just have to be right about it. Right? If you said x equals 2, that wouldn't be a counterexample, and why? Well, if I said x was equal to 2, well, what's x squared? 2 squared, which is 4. Well, is 4 greater than 2? Yeah, so that's not a counterexample, because that shows that it's true, you see? A counterexample is only something that shows the conjecture is false. Does that make sense? A counterexample. You get it? Yes, ma'am?
On the test, is it going to be like words like these kind of words, like Marcus doesn't play tennis, he plays football, or is it going to be numbers?
It could be either one. The
Will
point.
you tell us like what this is a counterexample, or we have to know what it
I
is?
would say, for instance, give a counterexample of the following conjecture.
So you'll tell us like, if it is a counterexample or not.
For instance, I would say something like this. Okay? I would say, give a counterexample. Counterexample for the conjecture. And the conjecture might be something like this. If x is less than 0, then x squared is less than 0. Right? So here's your conjecture, and then I say give a counterexample. And well, what's a good counterexample? You'd have to come up with it. Well, what's a good counterexample? Your answer would be, well, x equals -1. That would be your counterexample, and that's your whole answer. Why? Well, you don't even have to explain it, but look, -1 squared is equal to what? What happens when you square a negative number? Positive. -1 squared is +1, right? Is that less than 0? Is 1 less than 0?
Or couldn't
Yeah.
you just put any number?
It would have to be less than 0, though. You see, if I gave x
But
equal...
1 is not less than 0.
No, but, okay, this is what we're not understanding. The counterexample is x equals -1. Why? Because my conjecture says that if x is less than 0, then x squared is less than 0. You understand? It says if x is less than 0, then x squared is less than 0. You see? Well, my counterexample is x equals -1. Is x equal -1, is that less than 0? Yeah. So that's valid. That's a valid hypothesis. Well, but if I do x squared, that's -1 squared, which equals 1. And is 1 less than 0? No. So this shows that for some x's that are less than 0, x squared isn't less than 0. Does that make sense? So the whole point, guys, listen. The whole point, you have to show that this is false. I'm telling you, hey, if x is less than 0, then x squared is less than 0. And you're like, no, it's not. And I'm like, well, give me an example of where it's not true. And you're like, x is -1. You understand? You get it? Well, x is -1. Why? Well, -1 squared is +1. That's not less than 0. Do you understand? It's like, imagine you're like in an argument. You're like, well, I know that this is always true. And you're like, I know it's not true. Here's my counterexample. You understand? Does that make more sense, Olivia? Okay. Okay? So that's a counterexample. All right? That's what a counterexample is. All right, so next one, conditional statement. Conditional statement says, if P, then Q. All right? An example of that is, if I eat a banana, then I throw away a banana peel. Right?
Wasn't it if you give me your food, then I won't hurt you or something like that?
So it was at one point, right? What's the hypothesis of this one?
I eat a banana.
It's not if, it's I eat a banana. And be careful, guys. If you put if I eat a banana, I'm going to take off the point. Okay? So, because the hypothesis is not if I eat a banana. The hypothesis is I eat a banana. Okay? And what's the conclusion? I throw away a banana peel. You understand?
Do you want the odds, but not the F?
Never if and never then.
Okay.
Never if and never then. Okay? It's a simple statement. Hypothesis is a statement. I eat a banana, not if I eat a banana. Right? I throw away a banana peel, not then I throw away a banana peel. Get it? Okay? So those are the hypothesis and the conclusion. Okay? And I think we're pretty good on this, but remember, it could be of different forms, right? For instance, I could say, I only go to the movies if my friend goes with me. Okay? I only go to the movies if my friend goes with me. What's the hypothesis?
Go to the movies. I go to the movies.
My friend goes with me. Why? Listen.
Oh, because if is there.
Because if is after that. Look. I only go to, or even better, sorry than this, I don't want to be confusing. I go to the movies if my friend goes with me. Right?
I thought it was if and then.
It's not always if and then, though. The point is there's a hypothesis and a conclusion. The hypothesis is the thing that is the conclusion is the end of it, right? The end is I'm going to the movies, right? The end isn't my friend goes with me. That's what causes the conclusion, right? So the hypothesis, in this case, the hypothesis is actually my friend goes with me because it follows if. Right? The hypothesis always follows if. Okay? Sometimes if isn't there, but you've got to just be able to determine it. You understand? There's a conclusion to this. I go to the movies if my friend goes with me. Okay? Yes? hard to think of, but yeah.
Is it gonna be on
You like
one without it?
it's like I could have said the only way I go to the movies is I go to the movies when my friend goes with me, right? So it's like when my friend goes with me, then I go to the movies. Okay? If you're ever confused, try to turn it into an if-then, right? This isn't saying if I go to the movies, then my friend goes with me. No, it's saying I go to the movies if my friend goes with me, right? Does that make sense? All right, it's a little bit challenging here, but the point is it's always can be written as if and then, all right? All right, now look. So we have our conditional statement, if P then Q. What does the converse do? Swaps the hypothesis with the conclusion. Okay? So the hypothesis is I eat a banana. The conclusion is I throw away banana peel. So if I swap it, it becomes if I throw away banana peel, then I eat a banana. Converse swap. Swap the converse. Swap converse swap. Swap the converse. Swap the converse. I don't know. It's like your friend's got the black pair of Converses and you have the white pair of Converses, and you got a black outfit on that day and he's got a white, and you're like, yo, let's swap. So you swap the Converses. Got it? Right? Okay, so swap your Converses with your friend. Get a different pair, right? Okay, swap the Converses. So let's swap. You know, you got a red pair, your friend's got the blue pair, you're like, oh, I got blue, I rock that today. Right? There you go. Swap the Converses, right? Right? Okay, inverse is negate. You negate with the inverse. Inverse is negate. Okay? So negate means it's the opposite, right? So instead of if I eat a banana, it's if I don't eat a banana. And instead of I throw away a banana peel, it's I don't throw away a banana peel. See? So the inverse is negate. Okay? So converse is swap, inverse is negate. If I don't eat a banana, then I don't throw away a banana peel, right? You guys got to remember this, because just like on that quiz, on the test, it's just going to ask you for the converse. And you just got to be able to remember. Swap converse, right? That's an easy way to remember. And then inverse is the other one. What's the other one? Oh, negate, right? So inverse is negate, okay? And then the other thing is contrapositive. And contrapositive is the longest, so you do both, right? Converse, inverse, contrapositive. The longest word, you do both. You swap and negate. Got it? So it's if I don't, this is the conditional statement is if I eat a banana, then I throw away a banana peel. Contrapositive swaps it and negates it. So if I don't throw away a banana peel, then I don't eat a banana. You guys see that? Okay. Contrapositive is swap and negate. Does that make sense to you guys? Okay. Good.
Could it be did?
What?
Instead of if, can you use did?
For what? You make the whole sentence.
Like, did you see me eat a banana? Then I didn't eat. Then I didn't throw.
Could be.
banana.
And that's an example of like if I chose to make the test more confusing,
But,
right? You understand what I'm saying?
Yeah.
It'd be like in a conversation, it'd be like, did you see me eat that banana? Well, I must have not, thrown away, or did you see me throw away a banana peel? Then I must not have eaten a banana, right? Right? So that's like a conditional statement or a converse or something like that. But in a lot of cases, you'll have the if then. Does that make sense?
Yeah.
Okay. All right. So biconditional. What's the key for biconditional?
And if and only if.
if. If and only if. All right. And for a biconditional, it says the conditional statement and its converse must be true. Okay? The conditional statement, for instance, here is if I am the president, then I am the commander-in-chief. You see, it doesn't have the word then there, right? But it's implied that that's the conclusion, right? If I am the president, I am the commander-in-chief. It really should have the word then there. If I am the president, then I am the commander-in-chief. Okay, and the converse, remember, swap the converse, right? Swaps them. If I am commander-in-chief, then I am the president. Okay, first, the conditional statement. Is that true? If I'm the president, then I'm the commander-in-chief. Is that true? Yeah, right. If I'm the commander-in-chief, then I'm the president. Is that true? Yeah, sure is, usually, right? I don't know if there's any other example. I mean, I'm not a government teacher, but pretty sure the only commander-in-chief around is the president, right? Okay? So if you're the commander-in-chief, then you must be the president, right? Okay? So, well, that means the biconditional statement is true. I am the president if and only if I am the commander-in-chief, right? Okay? Because they're both true. Does that make sense to you guys? That's what a biconditional statement is. Now, it doesn't say if I am the president, then I am if and only if. No, don't be confused. There's no if then. It's just if and only if. Got it? That's a biconditional. It's if and only if. And by, you can remember, by conditional, two conditionals, right? It's the conditional and its converse, right? Does that make sense to you guys? Okay. So that's a biconditional statement. And what's the key for a biconditional statement?
If and only
If and only if. If and only if. Biconditional, if and only if. Yes.
For on the test,
Mhm.
is it gonna say what's biconditional and then you have to explain what it is?
No. Because if I ask you to explain what a biconditional
No, like
statement is.
if it don't have like, for example, a question like, if I am the president, then I am the commander in chief, and then it says do biconditional.
Yeah.
And then
Yeah.
you explain it.
You might say, what's the biconditional statement? Or if I give you the biconditional statement, I might ask you for the conditional statement and the converse, right? Which means you'd have to do it both ways, right? Understand? If I gave you this biconditional statement and asked you for the conditional statement, well, the conditional statement is just the first way. If I am the president, then I am the commander-in-chief. And the converse is the reverse, right? Swapped. Does that make sense? Kind of a little bit. Okay. All right. Now we get into algebraic proof. Okay? And remember, algebraic proof is when you're solving equations and giving the reasons, the justifications to the right of it. Remember that? So if I had like x plus 2 equals 7, and I needed to solve that equation, I would solve it and then use these justifications. So I've given you a list right here of all these properties of equality. Okay? You guys see that? So let me actually, hold on. Okay, that doesn't help you guys right now. You guys have that all on the same page, right? Yeah. Okay. So look, the properties of equality, you see them there? It's the addition property of equality. I add the same thing to both sides. When I add, it's the addition. Subtract the same thing to both sides, subtraction. Multiply both sides, multiplication. Divide both sides, division. Right? Yes, ma'am.
On the test, you're gonna have like are we gonna have to do the work and put it, or are you gonna have the work done and then?
Potentially you'll have to do the work and justify it. Okay? So you have to be ready to do that, and we're going to do that in a second. Okay? Reflexive property of equality is the same thing on both sides. A equals A. Right, Zoe? I tried to put words to them. I hope this helps you. Yes. All right?
Yes, it
Okay.
did. Thank
Reflexive, same thing on both sides. A equals A. Got it? Symmetric, the same thing flipped. Right? Like a butterfly wings or something. Butterfly wings. A equals B and B equals A. Transitive, guys, how many times did transitive come up in the past couple of lessons? Right? You gotta remember transitive, guys. You gotta remember transitive. Okay? If A equals B and B equals C, then A equals C. You cut out that middle one. That middle one is B, right? Okay? Alright, so let's do an example of this, okay? Make sure I'm still recording. What was that? So let's do an example of this. Alright, let's say we have 4. Oh, and also, class, before I continue on, remember there are other properties. There's the distributive property, substitution, and simplification. And I put here the properties of congruence are the reflexive, symmetric, and transitive properties of congruence are the same as for properties of equality, except with the congruent sign instead of an equal sign. Okay? Right? Okay, so we have to remember properties of congruence. Okay, but
so
then
it's
there's...
property of congruence when it has the squiggly sign.
Exactly. Well, squiggly. Exactly. All right. So let's do one. So 4x plus 3 equals 8. Okay? Yeah?
-2.
Close. All right.
No, it's -1.
Shh. Now, yes, ma'am? What's the first thing that I do? Distribute, right? So I distribute that 4 in. It becomes 4x plus 12 equals 8. And to the right of it, I have to give the justification. Well, what's the justification? Distributive property. No, you put distributive property. Justification is the distributive property, right? Now what do? I'm sorry. I subtract, right? I subtract what? 12 from both sides. And I end up with 4x equals 8 minus 12 is -4, right? 12 minus 8 is 4, so 8 minus 12 is -4. And how did I do that? What did I use?
Subtraction.
Subtraction, what?
Property of
Subtraction Subtraction property of equality. Right?
Then you divide both sides by 4.
Yeah, good. Okay, next step is, as Marcus was just saying, go ahead, sir.
You divide both sides by 4.
Good. Question? You guys? Good? Okay. See, I get to stand. You guys have to sit the whole time. Right? You can do some jumping jacks if you want.
I know,
No.
I'm so tired sitting down like this.
Can you put given in the first?
Oh, yes, sorry. This should be given. The first thing should always be given. Okay? Yeah. Now look. I have to divide both sides by 4, right?
Yep.
And I get x equals -1. And how did I get there? I divided, so it's the division property of equality, yes?
Simplify is when it looks like distributed, but you have to look really closely to see that.
Simplify, and this problem is done, okay? We're done. Simplify would be if I had like 2x plus 3x equals 10. And then you'd combine like terms, so it would be 5x equals 10, and the justification would be simplify. Does that make sense? Yeah, basically. It's like when you have like terms and you're combining like terms, that's when you simplify. Okay? Does that make sense? Good job, class. Hey, guess what, guys? It's the last class on a Friday. What?
What do you guys do?
That's what I'm talking about.
What are you doing this weekend?
Tonight I'm going to be here for the junior class fellowship gathering thing.
What time does that start?
do we have to go to them?
You're a junior, right?
Yeah.
Yeah.
Like
No.
it's like
You don't have
It's
to.
not like man.
But you
Oh,
probably
but it's
should.
Highly.
Yeah.
Highly. You really
What
should.
time does that start? Because I might be here.
6:30.
Oh, no, I'll be there.
Okay. I didn't mean to get us off track. Okay. Shh. Okay, check it out. Do you guys understand that?
Yes, sir.
You understand what we did? Okay, good.
Why did you
Shh. Okay, let's bring it back in. Sorry, guys. Sorry. That was my fault.
Why did you put distributive where it's subtract?
No. That's a very good question. Look, I put the justification next to the step where I've already got. How did I get to this place? I had to use the distributive property to get there. Does that make sense? How did I get to this place? I had to subtract to get there. How did I get to this place? I had to use the division property of equality. Okay, it's like, how did I get there? That's what I put next to it. Does that make sense?
How do you do that?
So
and then
look.
you put subtraction for division and then division for the one.
No. Because the thing is, you're looking ahead. Because you weren't. Look, if I didn't have any of this yet, I just had this step, and then I said, well, what do I do now? I distribute. And so once I distribute, then I put that right next to it. And then I said, well, what do I do now? Well, I subtract. You see this, Olivia? I subtract. Okay, so I put subtraction next to it. And then what do I do now? Oh, I divide, so I can put division next to it. Does that make sense? Okay, is that pretty clear to everybody? Okay, good. Now, next, geometric proof. All right?
Didn't we do that yesterday?
That's exactly what we did yesterday. So, geometric proof is a 2-column proof, which we get into in a second here. But we have to remember all these terms, okay? We have to remember all these things. All right, the first thing is definition of a midpoint.
Divides a line.
A definition of a midpoint is like this. Look, if I've got this line from here to here, right? This line segment from point A to point B, and I've got this midpoint. I've got this midpoint here, point M. Well, point M divides these two lines into congruent segments. That's the definition of a midpoint, right? It divides a line segment into 2 congruent line segments. Are you with me?
Yes, sir.
Yeah, Ernesto, you with me, sir?
Yes.
Okay.
Write this down.
Oh wait, hold on.
You can just draw a picture. It's already there. It's already there.
Oh wait, can I grab it?
It's written.
Oh.
It's written.
Yes.
Yeah, of course. So if you guys want to draw a picture like that, that's the definition of a midpoint. Oh, yeah, I'm going to be done in about 5 minutes. And then just remind me that, okay?
Oh, if when you're done, can I go
Use
use
the
the
bathroom.
bathroom? How'd you know?
I already know.
My stomach's like weird. I've used bathroom in every class.
It's all good, man. It's all good.
A little personal, Marcus.
You just gotta look. You know what? When you gotta go, you gotta go. You know, that's all. That's my theory on it. You know,
The teachers
and
get
we
so
might
mad
have
at
to
you.
prove that using some deductive reasoning, maybe some inductive. Which inductive reasoning is with patterns, and deductive reasoning is with
Facts.
logic.
I mean,
Logic, right? Cool, man. All right, here we go. Using it already in real life. All right. Definition of an angle bisector. All right, what's the definition of an angle bisector?
Isn't it cut an angle in half?
It cuts an angle in half.
That's right. An angle bisector. Say I've got this angle here.
Because it's better to write it than just because when you personally
I just
write
laughed
it,
so
like,
bad.
Shh, shh, shh. Guys, so here's this angle ABC, right? And let's say I have an angle bisector here. Okay, well, what does this angle bisector do?
Cut it in half.
It cuts it in half, but a more mathematical way of describing it would be it bisects it, which means it splits it into 2
Congruent.
congruent angles. Okay, so if you want to draw that picture, you can go right ahead and take some time and draw that. That's the definition of an angle bisector. It splits an angle into 2 congruent angles. All right?
No,
Yes, for
that's
sure.
like a train, bro.
So that's the definition of an angle bisector. Okay. We move on. Definition of congruent angles. Well, 2 congruent angles, their measures are equal. So what is that kind of like? Well, for instance, in this case, if I said this was D here, then I might say, look, class, everyone pay attention.
A, B, D, and D.
Angle A, look, A, B, D. Remember how to name angles,
Yeah.
guys? A, B, D. Angle A, B, D is congruent to what angle? Angle D, B, C, right?
Oh, D, B, C.
Or CBD, right? DBC, which means that the measure of ABD is equal to the measure of DBC. See? And that's because of the definition of congruent angles. The definition of congruent angles says if 2 angles are congruent, then their measures are equal. That is the definition of congruent angles. Okay? And these are all things that we would use in our two-column proof, right? These are all the things that we would use as our reasons. Okay? Any questions on this?
No, sir.
Okay, next one. Definition of a right angle, right?
It's not me.
If an angle is a right, yes? Go ahead. If an angle is a right angle, then it is equal to 90 degrees. We know this, okay? Definition of supplementary angles. Shh. If two angles are supplementary, then they what? Add up to 180 degrees.
What was supplementary again? I mean,
Complementary
Complementary, that's 90, right?
adds up to 90 degrees.
that's complementary right angle.
No. Complementary angles are two angles that add up to 90 degrees. A right angle is one angle that is 90 degrees.
Wait,
We have
complementary
to
is
know
not-
complementary.
Right. There's a reason why they're called. Okay? You should know complementary are two angles that add up to 90
It's
degrees.
just confusing.
But just focus on
Remember
what's
C
there.
becomes before like
S. Good.
or S or whatever?
Okay. Now, the one thing that's a little bit, now look, everyone pay attention. If you've tuned out, if you've jumbled your mind a little bit, tune back in. Okay? The definition of a right angle is it's 90 degrees. The definition of supplementary angles are two angles that add up to 180 degrees. The linear pair theorem says that if two angles are in a linear pair, then they are supplementary. Okay? So what does this look like? Okay, what does this look like? That's the question right now. What does the linear pair theorem look like?
Wait, so obtuse is 180.
Obtuse is more than
More than 90.
90. Look. All right. Look at this, guys. Look at this. Let's tune in. Okay. So I've got this line here. And I've got these two angles, and I say that this is angle 1. This is angle 1.
This is the
And-
linear pair theorem.
Yes. And this is angle 2. Guys, let's tune in. If this is angle 1 and this is angle 2, they make up do these two angles make up a linear pair?
Yes.
Yeah.
Why?
Because they both add 180.
They make a straight line. That's what a linear pair is. They make a straight line, right? Well, what else do I know? If they make up a straight line, then they add up to what? 180 degrees. So what this tells us is that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. They're a linear pair, which means they are supplementary, okay, which means they add up to 180 degrees. Now you have to be careful. You can't go directly from linear pair to add up to 180 degrees. I could say, first, I would say angle 1 and angle 2 are supplementary. And why? Because of the linear pair theorem. Right? Why? Because of the linear pair theorem. And then I would say the measure of angle 1 plus the measure of angle 2 adds up to 180 degrees. And how do I know that? Well, I just said they're supplementary, so that's the definition of supplementary.
Do we have to explain it to you like that?
That would be in a two-column proof. Remember we went all over two-column proofs yesterday?
Yeah.
That's the deal of two-column proofs, right? I would say angle 1 and angle 2 are a linear pair, right? Here, let's do that actually.
So would that be always right given or linear pair?
Yeah, let's do that actually. Hold on. I'm gonna actually do a whole two-column proof for you guys with this. Okay? So you can see an example. So I would say, for instance, given angle 1 and angle 2 are a linear pair, and I would say prove that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. Okay? This is a very simple example. Now look, on a 2-column proof, I have the statements on the right and the reason on the statements on the left, reason on the right. Statement on the left, reason on the right. Reason right, right, R, reason right. Got it? Statement on the left, reason on the right. Okay? So this would be my 2-column proof here, okay? Well, my first statement would be what?
32 equal.
Angle 1 and
Angle 1 and angle
angle 2.
2 are a linear pair. And what's the reason for that?
They equal 180.
It's given.
Oh, never mind.
The first reason is always going to be given, guys. First reason is always going to be given. You understand that? First reason is always going to be given. Yes, sir?
Oh, I have 2 questions.
Okay.
One, like, I use the restroom, and if I can take a picture of that.
1, no, 2, yes. All right. Angle 1 and angle 2 are a linear pair. The first reason is given. All right. Well, if they are a linear pair, what's the next thing that I know? That they are what?
180.
No, I can't know that yet.
Linear.
If 2 angles are a linear pair,
They're next to.
then they are what? What does it say right there on your paper? Linear pair theorem says what?
Supplementary.
Then they are supplementary. Angle 1
Oh.
and angle 2 are supplementary. And what's the reason for that?
Linear pair theorem.
That's the linear pair theorem. You guys understand that? Okay. Now, if I know angle 1 and angle 2 are supplementary, what do I know about them?
They equal 180 degrees.
They add up to 180 degrees. Measure of angle 1 plus measure of angle 2 equals 180 degrees. Does that make sense? Yeah?
Yes.
Okay, and how do I know that? How do I know that? Definition of
Oh.
Oh, definition of a linear pair.
supplementary.
Pair.
The definition of supplementary. That's the definition of supplementary.
Isn't a linear pair 180 though? Or is that the linear pair theorem thing?
The linear pair theorem says that if they're in a linear pair, then they're supplementary.
Okay.
And then you have to go to the next step, which is if they're supplementary, then they add it to 180. Okay? Does that make sense?
Yeah.
Are you guys with me? 2-column proof?
Yeah.
We on the same page? Olivia, how you doing? You been able to pay attention?
Can I run to the toilet now, please?
All right, yes, go, Ernesto, go. Anybody, you guys can go, yeah, go.
The whole class is just.
No, the whole class doesn't get to just
Like
go.
a good walk around, like a good lap.
Yeah.
Can I just get a good
Can I
lap?
through the window?
We,
Like,
we didn't
please,
break.
my
You guys stand up. You guys can all stand up and stretch. Yes, ma'am?
Yes.
Can I get water?
Hold on. Yes, go ahead. Just go. Come back quickly, though.
Can I get the bathroom?